In this video I'm going to be looking at enthalpy cycles. Enthalpy cycles, also known as thermochemical cycles or sometimes Hess cycles, are used to indirectly find the enthalpy change for a reaction. But if I were to ask you what is an enthalpy change, what would your answer be? We know that we can show enthalpy change as delta H. For a reaction it would be delta RH, and the bus stop sign, which indicates it's being done under standard conditions, 298 K and 100 kilopascals. But at GCSE we use the term enthalpy maybe in place of energy and vice versa, but they're not actually the same. An enthalpy change, delta H, is the heat transferred at constant pressure by a chemical reaction. By constant pressure, we invariably mean atmospheric pressure, because nearly all chemical reactions are open systems. Heat is able to be transferred from the surroundings to the system and vice versa. So if we take my little reaction here, I have got some powdered zinc, I've got some copper sulfate solution, and if I were to put the spatula of zinc into the copper sulfate and stir, the temperature would go up. This is an example of an exothermic reaction. And what is actually happening is that the heat from the chemical reaction is being transferred from the system to the surroundings. And that is why the temperature is increasing. And we know that heat changes are the result of bond making and bond breaking in chemical reactions, but I'm not going to go into that at this point. That is the focus for a separate video. Now, our enthalpy change depends only on the final initial conditions of the system, and it's independent of the route taken. So let's have a look at what I mean by that. My example is the oxidation of carbon graphite to form carbon dioxide. Now, I can react carbon directly with oxygen to make carbon dioxide. And I can measure that enthalpy change. It would be enthalpy change of combustion. And we find that to be minus 393 kilojoules per mole. So as expected from a combustion reaction, it is pretty exothermic. But that's not the only way to get from carbon to carbon dioxide. I could partially oxidize the carbon, so incomplete rather than complete combustion, to make carbon monoxide, in which case I have a little oxygen left over. And then I could use this oxygen to oxidize the carbon monoxide to carbon dioxide. And once again, I can measure the enthalpy change of reaction for each of these reactions. So carbon to carbon monoxide is minus 110.5 kilojoules per mole. And oxidizing carbon monoxide to carbon dioxide is minus 283 kilojoules per mole. I should have said that was 393.5. I'm just going to squeeze that in there, because what we should hopefully see is whether I take, and I'm going to call that route 1, or I take route 2, the enthalpy change, the complete enthalpy change for this reaction, is the same either way, because the initial and final conditions are the same. In both cases I start with solid carbon graphite and oxygen gas, and in both cases I end up with gaseous carbon dioxide. So the key here is that the enthalpy change is independent of the route taken, as long as the initial and final conditions are the same. This is also known as Hess's law, and we can use this idea to calculate the enthalpy change for a reaction where we can't actually carry out the reaction directly. Let me give you an example of a reaction where we can't measure the enthalpy change directly. Very simple. We're going to react carbon with hydrogen to make ethane, C2H6 gas. So why can't I measure this enthalpy change directly? Well, there's a couple of good reasons. Firstly, under standard conditions, which is obviously room temperature and pressure, carbon and hydrogen don't react. It requires a huge amount of heat. Secondly, when we get carbon and hydrogen to react, it's not necessarily so that we are going to make ethane. We could make any number of molecules composed of carbon and hydrogen. Methane, for example. Benzene. So, if we can't measure this enthalpy change directly, maybe we can take an alternative route and look at the enthalpy changes involved in the alternative route to come up with a value indirectly for this enthalpy change. And this is essentially using Hess's law and an enthalpy or Hess cycle or thermochemical cycle to calculate the enthalpy change for a reaction. At A level, there are two enthalpy changes that are routinely used as an alternative route to directly find the enthalpy change for a reaction. First one is the enthalpy change of formation. So F stands for formation. Now I'm giving you the full definition here. You need to learn your definitions. That's absolutely crucial. So the first big thing at A level, learn your definitions for enthalpy changes. So enthalpy change formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. And enthalpy changes always refer to a particular equation. So let's look at the enthalpy of formation of ammonia, NH3. So we know ammonia, NH3. It's the formation of 1 mole of a compound. So I need to be careful when I'm writing my equation that I end up with 1 mole of NH3. And this has an effect on how I balance it. So to make ammonia from the elements in their standard states, I would need nitrogen gas and hydrogen gas. I only need 1 nitrogen, so that's going to be half N2. And I need 3 hydrogen atoms, so that's going to be 1.5, and just squeeze that in, H2. So we need to be very clear here. The enthalpy change of formation for this is minus 46.1 kilojoules per mole. And once again, this value is associated with 1 mole of ammonia. If I'm making 2 moles of ammonia, the enthalpy change would be minus 92.2 kilojoules per mole. The second enthalpy change that we need to know is the standard enthalpy change of combustion. So C stands for combustion. And this is the enthalpy change of 1 mole of a substance, so it could be an element or a compound, in its standard state reacts completely with oxygen gas under standard conditions. So 1 mole of a substance, we could take a mole of methane, for example, and react it with oxygen, complete combustion, to make carbon dioxide and water. And the enthalpy change for this reaction is minus 890 kilojoules per mole. So as expected, it's a very exothermic reaction. When we're writing our equation, our elements, our substances, our reactants, our products must be in their standard states under standard conditions, which means that water at atmospheric pressure and room temperature is a liquid, not a gas, despite this being a combustion reaction. And that's a very common point at which people get tripped up. Now we come to looking at an actual enthalpy cycle. And this enthalpy cycle uses enthalpy of formation data. To calculate the enthalpy change for the reaction, it's a reaction between iron oxide and ammonia, given the following data. So how are we going to go about this? There are hundreds, probably thousands of different ways in which enthalpy cycles are taught. Over my many years of experience, I have come up with a method that is genuinely foolproof. You cannot go wrong. So if this is something you struggle with, then please pay real attention, maybe make some notes on this particular method. So first of all, I start off by writing out my top equation. My top equation is the one that's being given here. So it is 3 Fe2O3, I'm not going to bother with state symbols, reacting with ammonia to form 6 FeO and 3 water and a nitrogen. And we will notice that we have got enthalpy of formation, I know that because it's got a little F, for iron oxide, for ammonia, for water, but not for nitrogen. Why? Because nitrogen is an element. So enthalpy of formation is the enthalpy change for the formation of 1 mole of a compound from its elements. So I'm not expecting there to be any data for nitrogen gas. So looking at our cycle, once again, this is why we need to know our definitions. So enthalpy of formation, this data is for the formation of 1 mole of a compound. So the formation of iron oxide, the formation of ammonia, the formation of water from their elements. So that tells me that the bottom line of my cycle needs to be the relevant elements. Again, make sure that you've got your head screwed on and that you're writing the elements in their standard states under standard conditions. Okay, so what do I know? That I am making 3 lots of Fe2O3. That's 6 iron atoms. So along the bottom here, I'm going to have 6 Fe. It's really common, because I think it's written often in the top equation, for students to write, I'm going to need 3 Fe2. Well, iron doesn't exist as a diatomic molecule, so straight away that is complete rubbish. So we don't want to have that in our cycle. So it's 6 iron atoms. I also need 9 oxygen atoms. 3 times, wait a minute, I've got my pen back, 3 times 3 is 9. Oxygen is a diatomic gas, so that would be 4.5 O2s. So we need our elements in their standard states under standard conditions, which means also need state symbols. If I were writing this out for, and part of the exam question was to write the cycle out, you would definitely put your state symbols in, so I'll put them in along the bottom. I should stop being so lazy, shouldn't I? I need 2 nitrogen atoms, and nitrogen is a gas as an element. And I am going to need 2 times 3, 6 hydrogen atoms. Once again, hydrogen is a diatomic molecule, so that would be 3H2. So now I have the relevant elements in the right amounts in their natural states as elements. Let's go back to this definition. Formation is the formation of 1 mole of a compound from its elements. So we're going from the elements to the compounds. From the elements to the compounds. So the key here is that each part of the cycle makes sense and it should automatically balance. So we have 6 iron, 4.5 oxygen, an N2 and 3H2 making 3 Fe2O3 and 2 NH3. And we have these same elements here also making 6 FeO, 3 H2O and an N2. Whichever way I look at this cycle, each equation individually balances and makes sense. So now let's put some numbers in. I know that the enthalpy formation for 1 mole of iron oxide is minus 824. I'm making 3 moles of iron oxide, so it'd be 3 times minus 824. So I'm putting this information on the relevant arrows for the relevant equations. I'm also going to make 2 ammonia. So I'm going to need 2 lots of minus 46. That would be the enthalpy change to make my iron oxide and my ammonia. Looking at my other arrow, I can see that I'm going to make 6 FeOs. So I need 6 times minus 266 and 3 lots of water. So 3 times minus 286, and we've already explained why there's no number for nitrogen. So far so good. Most students don't have a problem up until this point. Let's have a look. So I've got root 1, and root 1 is finding the enthalpy change of reaction. That's what the question's asking us. And then I've got root 2. And root 2 is taking us from our reactants to our products via the elements. Root 2. So how do I go about calculating a value for delta RH? So this is the foolproof method, delta RH. First thing you do is you write down the numbers in the order that you have them on your arrows. So it's going to be 3 times minus 824. You put a plus sign between each, it's going to add them all together, plus 2 lots of minus 46, plus 6 lots of minus 266, plus 3 lots of minus 286. Okay, don't get your calculator out yet. Now, root 2 involves going from these compounds here to their elements, then using these elements to make new compounds. So if making a compound is exothermic, unmaking it is going to be endothermic. So I know that I don't want my arrow, I don't want to go from elements to compounds. What I actually want to do is go from compounds to elements. So I will reverse the sign on these two numbers, because if making the compound is exothermic, breaking it down is going to be endothermic. And I'm going to change the sign in my line down here in my actual calculation. On the second arrow, my root goes in the same direction as the arrow is written in the cycle. So these two numbers are correct. They stay negative. I then plug this calculation directly, as written, into my calculator. So 3 lots of plus 284, plus 2 lots of plus 46, plus 6 lots of minus 266, plus 3 lots of minus 286, and you should come out with plus 110 kilojoules per mole. Always, always, always put the sign in. In this case, it's an endothermic reaction. Now, compare this with a question that asks us to find the enthalpy change of a reaction, but it gives us enthalpy of combustion data. Now, enthalpy of combustion data, these values here are for the combustion of 1 mole of a compound or a substance completely in oxygen. So I'm going to start in the same way. I'm going to use my equation to write my top line. So I have CH3CHO. Shan't be lazy this time. I shall put my state symbols in, reacting with hydrogen to make CH3CH2OH. Now, combustion. If I burn a molecule containing carbon and hydrogen and oxygen, I'm going to end up with carbon dioxide and water. So I know that the bottom line of this cycle is carbon dioxide and water in their standard states under standard conditions. So despite this being a combustion reaction, water needs to be identified as a liquid. If I'm burning these substances to make carbon dioxide and water, then I'm going from the substances to the carbon dioxide and water. in each case. So once again, each equation within my cycle must make sense, and it needs to be balanced. So 2 carbons would give me 2 carbon dioxides, and 1, 2, 3, 4, 5, 6 hydrogens altogether in my reactants would give me 3 lots of water. Let's look at the numbers. So the numbers here, if I were to completely combust 1 mole of ethanol, it would be minus 1167 kilojoules per mole. And if I were to combust a mole of hydrogen, minus 286. Now my equation only has 1 mole of each, so I don't need to multiply these up. And burning a mole of ethanol to form carbon dioxide and water would release 1367 kilojoules per mole. So let's have a look. Root 1 is the enthalpy change of reaction that we are trying to find. Route 2 takes us from the reactants to the products via the combustion products. So this is route 2. So once again, I'm going to write out my numbers exactly as they are. So delta RH is going to equal minus 1167 plus minus 286 plus 1367, so plus minus 1367. So I've made no changes at this point in time. Now I'm going to check my route. To begin with, I'm moving in the same direction as the arrow in my cycle. Route 2 follows the arrow in the cycle. So these numbers are correct. The second part of route 2 goes in the opposite direction to the arrow in the cycle. So this number is not correct. It needs to be positive. If we think about it, we're kind of unburning ethanol. So if I change the number up here, I then change the number, the sign on the number, in my calculation. And then I plug it directly into my calculator. So minus 1167 plus minus 286 plus 1367. And that comes out to be minus 86 kilojoules per mole. So let me finish by just recapping or summarising the way that these cycles are drawn out. So step 1 is to write out your equation for the reaction for which we're trying to find the enthalpy change. You write out exactly as it's given in the question. Step 2 is to look and see whether the data you've been given to construct this cycle is enthalpy of combustion or enthalpy of formation. If it's enthalpy of combustion data, then my bottom line is going to be carbon dioxide and water. If it's an enthalpy of formation data, then my bottom line is going to be the elements in their standard states under standard conditions and balanced accordingly and state symbols accordingly. So for combustion, that tends to be the water as a liquid, not a gas, that throws most students. I then need to decide on which way my arrows are going in my cycle. So I'm just going to clean this up slightly so I know what, you can see what I'm doing. Where's my eraser gone? There we go. So for combustion, I am burning my substance. My substance is going from being a substance to carbon dioxide and water. From being a substance to carbon dioxide and water. So my arrows are going down. If I were... Why is this not going backwards? Right, unfrozen my screen. If this were an enthalpy cycle using formation data, so we've got our elements on the bottom row, then again, you need to know your definitions, then we are forming compounds from their elements. So the arrows go up because we're going from elements to compounds, from elements to compounds. You then write your numbers on each arrow, and in each case it's exactly the same as the data that you've been given in order to construct this enthalpy cycle. Then you draw in your second route, route 2. and compare the way that your route 2 goes to the arrows that you've drawn on your cycle. So where the route goes in the opposite direction to the arrow, we are going to have to change the sign. Where the route goes in the same direction as the arrow on your cycle, then, as we can see here, the signs are correct. Write out your calculation and plug it into your calculator exactly as you've written it. One of the things that students tend to ask or try and remember is that arrows go down for combustion, arrows go up for formation, and they get in the exam and they're under pressure and they forget, because they're just learning stuff parrot fashion. You've got to have a clear understanding of the definition, and if you have that, you can automatically always work out which ways the arrows go, and you're not going to get yourself in a muddle. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.